Welcome everyone to 321 Gang's webcast, Building Really Big Systems with Lean Agile Practices. My name is Kara Rawlings and I'd like to tell you a little bit about 321 Gang before we get started. 321 Gang has many years of experience successfully deploying enterprise-scale development tooling and processes in support of software and cyber-physical system builders. In 2014, we launched our SAFE training and transformation business and even contributed to the development of the framework. We focus specifically on software and systems engineering tools and processes. I'd like to introduce our presenter, Harry Kahneman. Harry used to be with 321 Gang. He actually was one of our founders. And now he is a SAFE fellow and principal consultant at Scaled Agile, where he helps organizations build and deliver solutions faster, more predictably, and with high quality. He has spent the past 2 decades consulting with aerospace, defense, automotive, and other organizations to adopt better engineering practices, including Lean, Agile, MBSE, requirements management, quality management, and the related activities necessary to support compliance. Harry is a regular presenter on the Lean Agile topics and engineering practices at Agile, Systems Engineering, and government conferences. Please take note of your question box in your control panel. We'll be accepting and addressing questions throughout the presentation. So feel free to type them in as you think of them, and Harry's willing to address them as we go. And Harry, the floor is yours.
All right, great. Thanks, Carol. You guys can hear me and see my screen, right? We're all good? I'll take that as a yes. Perfect. Great. So excited to talk today about building really big systems with Lean Agile practices. We've been seeing a big uptake from a lot of industries. Certainly Agile has, pervaded the software community for the last 2 decades, easily 2 decades. It's become basically the de facto standard. But the cyber physical system builders, the big system builders in aerospace and defense and automotive and missiles and medical devices, right? They haven't seen the need, or the software folks have seen the need, but the product, the rest of the product development, mechanical, electrical, all the other engineering disciplines haven't really. We've been more pushing it into those disciplines and seeing a pull from them. My experience over the last year and a half or so is we're seeing a strong pull, certainly from industries like automotive, seeing it more in aerospace. That it's not just the software, we're being pulled into those organizations to go help their hardware folks. So very excited to see that being a trend today. So I want to talk about, how does it apply? How does it apply to these really big systems that have a bunch of suppliers and a bunch of other components besides just software? And that's really our goal today. We already introduced me, so I can jump past that. So the agenda today is we have to start with why, right? Why do we want to change? What is the reason that we're making this change in our engineering practices? Then we'll explain what really Agile product development is. It's not really Agile software development. It's really more Agile product development. Then we'll focus on 4 specific practices. We'll talk more about those when we get there. So let's jump into the first topic. This is really the why. Why do we want to change? Why do we have to build our systems differently and think differently about how we plan, design, specify, construct our types of systems? So been talking about the race for flight. The last year I've used this as kind of a metaphor for the challenge, right? And most people don't recognize this image. I always ask in a conference, what is this? And a couple people will know who it is, but not everybody. So here we are back in October of 1903, and this is Mr. Langley, who was trying to make the first airplane, first aircraft. So any pilots out there, you probably recognize this because you would know. But he had a lot of experience with astronomy and space. He was well funded by the Smithsonian Institute, but fundamentally it would never fly. In fact, this is what happened on his first flight, right? The Smithsonian Institute funded him over $50,000. This is a lot for 100 plus years ago. The plane was never going to fly because it had fundamental flaws in the design. It could never create enough lift for the mass of the plane to actually fly. Now let's contrast that approach to that of the Wright brothers. I'll ask, who is this? And of course, everybody knows who this is. And note that they were 2 months apart. While Langley was crashing into, I think it was the Potomac River, the Wright brothers were successfully flying down a Kitty Hawk. One was well funded. One was a scientist and an engineer. One was well funded, had a huge staff to help him design, build the best aircraft he could. The other two guys were bike folks, right? They ran a bicycle shop. But what did they do instead? Well, they focused on the barriers to flight. They knew that well, we have to make lift. How are we going to find out if we're making lift or not? Well, let's start experimenting with different wing shapes and wing foil shapes, and let's build some test equipment like the world's first wind tunnel to try those shapes out. And when we think we've got the right shape, let's build a mock-up. Let's build a prototype like a kite. We'll build a kite in the shape of our plane to see what kind of lift it can generate. We'll throw bags of hay on it and see if it can support weight. So they iteratively learned and experimented to learn more about flying. They didn't try to design a plane. They tried to learn about flight, and that's fundamentally different. So let's take a little shift here. Let's look at the digital age and talk more about that. This is research done by Carlota Perez. It's about 200 years old now. I'm sorry, it's about 20 years old now. This is research from the early 2000s, 2002, I believe. And in her research, she looked at basic influxes of capital, large events that occurred that disrupted the status quo for a lot of industries. Industrial revolution, the invention of steam and railways, the invention of oil and mass production and automotive, right back in the turn of the century, right around this time the Wright brothers and Langley were flying their planes. So at any one of those times, capital was flowing in. Like in Detroit alone, I think in the 1920s or 30s, there were 200 or 300 automotive companies in Detroit alone, right? And of course, there's then this turning point where the winners emerge, right? They figure it out and they beat everybody else to market, and they're widely successful, right? And it takes another almost turning event for them to lose their dominance. And so she posited that, are we at the turning point in the digital age, right? This is back in 2002, 2003. We're in that turning point, and certainly we probably were for certain industries. We all shopping for Christmas this year. How many of us are going to stores versus shopping at Amazon, right? I don't think that anyone's gonna disrupt Amazon and digital retail anytime soon. Right? That winner has emerged, that victor has emerged, and other industries, Spotify and Apple for music. Could someone else enter? Maybe, but the digital music has probably been, that landscape has been resolved as well. However, we look to the systems we build: aerospace, automotive, avionics, medical devices. We're still seeing, in fact, I think we're beginning to see, or have begun to see the last few years, massive amounts of capital being influxed into there, right? What is transportation going to look like in 5 years or 10 years? It may not look like it looks today, and that's a digital transformation that's going on in that industry, right? So we're still seeing those transformations. But really fundamentally, Carlota didn't just talk about the fact that there was disruption associated with these ages. Certainly there was, capital influx, the victors emerged, and they were the incumbents until some other event occurred. She also noted that each one of those revolutions included a change to the people, how they were organized, what kind of skills were necessary, how we managed the work and how we managed the people, right? This is where we discovered Taylorism, or Taylor was invented, right, around steel. There were leaders that trained other people how to do the work. They supervised the work, right? That's where we got project management from. I'm a project manager, and I'm going to supervise the work. I'm going to tell you the work you need to perform. You can perform the work, but I'm going to tell you what the work is, right? That contrast to Agile, where we give, we'll talk later about giving them an administrational goal, and they define what work they need to do to meet that goal, right? So we're gonna, if we look at the different management methods, the one has not been, there's no management method yet for the digital age. What do managers do? What does a manager look like? We think we have in SAFE, we have courses on management and the leading by example, leading in the digital age. We have some training that's emerging that's trying to posit this new approach to how we manage people and manage the work. But we're going to really posit that the focus of that management style is one that focuses on learning, right? The organizations and the industry, the organizations that learn the fastest will be the ones that are victorious in this next digital age. Also, I should point out that also we're managing a different kind of worker here. That all of those other disruptions really favored labor workers, right? They were labor workers. We could teach people how to do the work. In the digital age, the disruption really is affecting knowledge workers, right? And the knowledge worker knows more about the manager, right? The person that manages them. So it's a different way we manage those people. So this change is even more dramatic than the other changes, than the other revolutions, I want to point out. So if we looked at kind of a lean agile view of incremental learning, if we looked at the Wright brothers kind of from a safe perspective, we certainly have a solution, and that solution is going to evolve based on learning. It starts out as wireframes and diagrams and maybe some equations and forcing and functions. And then there's some prototyping done with wind tunnels. That's like the old wind tunnel the Wright brothers had, where old foil shapes. Then we make prototypes like a kite, another prototype like a glider. And each time we're validating, we have a roadmap of things we need to learn, right? We have to determine how to do lift. How are we going to control the plane? Once we get lift, we have to be able to turn left and right, go up and down, and things like that, not crash. Then once we can control the plane, we have to add propulsion to be able to make a flying machine. And there's so that roadmap has the anticipated milestones we choose to accomplish. And then there's a backlog of work laid out and some timeline about how we plan to get that work done and achieve that goal at the end. So this is explaining basically what continuous learning looks like. How do we build a solution based on learning and learning cycles? All right. So next thing I want to talk about is explaining agile product development. Certainly the roots of agile are not in software. Software got to the agile concepts first, but really agile is about product development. If you look at the roots of agile, they come from an article back in the mid 80s published in the Harvard Business Review called The New Product Development Game. And in that's where the term Scrum comes from, because they were contrasting the old way of product development, where there was one group that specified the requirements, and they were like a relay. They would do the requirements part of the race. They would hand the baton off to the designers, and the designers would do their designs. And they'd hand the baton off to the implementers, and then the testers, and then the product release people. So there was all these milestones along the way of requirements and design implementation for products. And then they looked at how these other companies, we'll talk about them in a minute, were building products. They said it's more like a rugby team, more like a scrum. The rugby team, all the players were involved all the time, and they had a common goal of trying to move the ball downfield towards the goal, right? So instead of a handoff to move the baton forward, it was everybody working together to move the ball down the field. And if you notice, every one of those, this is back in the mid 80s. There weren't a lot of products that had a lot of software in them, right? There were photocopiers, and there were cameras, and NEC things, and so they looked at those products and said, what are some common characteristics? Well, there was built-in instability, right? The leader set a vision with a challenging goal, but gave teams the freedom to actually design and implement, and they defined their own work. It wasn't the leader, like a traditional project management, coming up with a plan and a schedule to build a product and saying, teams do this, right? The teams have the knowledge, not the manager, right? They know more about the work. So we have to let the teams plan their own work, right? And this is the beginning of that concept in Agile, right? Built-in instability. Self-organizing teams, right? There were autonomous teams. There were cross-functional. We call that cross-functional today. Overlapping development phases. We didn't have a big requirements effort, design effort, implementation effort, right? They looked at that. Back then they called it overlapping phases. So this is really the roots. I'm not going to through them all, but this is the roots of Agile development. Apparently, the software people read this article first, about 10 years later, in 96 or so, and started applying it. Actually, the Scrum practice started in the early mid-90s. So the software people picked up on this and revolutionized how we build software products. We have to pick up now and realize that it's not just for software products, it's for all product development. So this is fundamentally Agile Products' goal, is to deliver quickly so we can get fast feedback. Every system that we're going to build is highly innovative. It's never been built before. And we haven't done this thing before, so we don't really know how to build it. It's not like building a house where we built the same house last week. We can build another house this week. So Agile wants to build something quickly to get feedback. There's technical uncertainty that we have to validate. There is user uncertainty. There's market uncertainty. The faster we can build something to get it into an environment where we can test all those assumptions, technical assumptions, market assumptions, business assumptions, end user assumptions, the faster we can get feedback on that, the better the more likely we are to get a valuable product and build the right product for the right customer. So that's the goal really of Agile. If you look at the waterfall approach, the Big Bang approach up top, that we have one cycle to learn. That's one learning cycle. incremental delivery, we have much more learning cycles, many more learning cycles. We can learn faster, we can make adjustments. So why do we build these cross-functional agile teams? Because they're optimized to deliver quickly. It's harder to get 100 people to deliver something than it is to get 8, or 1,000 people to deliver something than it is to get 8. So let's start with this. Agile teams are optimized to deliver quickly. They have all the skills necessary to define their own work, right? We don't have to wait for somebody to specify what I'm going to build. I've got a product owner. The product owner knows what we're going to build. We don't have to wait. We have that authority. And then they have all the skills necessary to build it, test it, deploy it, potentially operate it as well. So they're optimized to go deliver quickly. When we build big systems, we typically need more than one 8-person team. We need many teams and even many value streams of many teams. We'll talk about that in a couple more slides. But and this is really where SAFE has made its mark, I think, in the industry, right? How do we scale a team of a small agile team to something that's more valuable to big organizations? And that's really a thing we call the agile release train. It's a team of agile teams, and we scale all the well-known roles, events, practices to a much higher level. So you have 100 or so people, 125 people now building something, and this has been widely successful in the industry for the last decade or so, proven method. But really, these agile release trains, these team of teams, if we think about them, they are what we call a development value stream. That's those great things down there. They're optimized and have all the skills and resource authority necessary to produce solutions, right? And these solutions here, I'll grab my pen, right? These solutions here, so we have these development value streams that are producing various solutions. Well, those solutions are what make money for our business. Up here, we have a different kind of value stream, the operational value stream. And this is where the customer sits here. And this is a loan example, right? You can look at it. So this is the journey of a customer off to go apply for a loan, get a loan, repay the loan over time, right? And there's certain systems that need to be developed along the way to make that happen. Let's look at a big system example of that operational and development value stream. Certainly we have so this is an example of a vehicle, of an automotive example, where we've got an autonomous delivery system, where we have a rider who wants to go from some location to a destination. So what the activities we have to perform, then we have to plan their route, we have to get them there, we have to track the journey along the way, maybe in my mobile app, or I'm sharing the ride with my friend or my mom who I'm going to come visit. And then we can get assistance along the way, right? We need support along the way. So certainly some of these things like route planning and traffic, that could be a development value stream. That could be in SAFE, what we call an agile release train, or if it's too big for that, we have a thing called we have a really big agile release train called a solution train. So that could be built by 100 people, 200 people, something like that. But when we look at this vehicle, that's a really big thing. That's not a couple hundred people. That's a couple thousand people, or actually it's probably maybe in the tens of thousands of people. When you look at all the suppliers and across the supply chain where that occurs. So certainly this is a different beast in terms of thinking about development value streams. So when we think about that all of us are down here somewhere in big system building, somewhere in the bowels of this supply chain, right? We are an internal supplier, we're an external supplier. Our part here is going to be given to somebody who gives it to somebody, eventually puts it in a car. All of us collectively have a shared set of end users out here, customers out here. If I think of this as from use case modeling, these are all the actors that are at the end of the system that we have to design the system for. We have to design support or interface or some way to enable them to support them. They have certainly the infotainment system here. The rider is going to be a critical customer, right? Because they're going to interact directly with the end user of that. But that infotainment system also has to be manufactured. So when we consider the design of the infotainment system, we consider manufacturing. We consider the operational side. How are we going to make updates, or how are we going to do maintenance on this infotainment system? Nowadays our cars are kind of like our phones. I don't want to just buy a car and have its functionality be static for the rest of its life. I expect to get over-the-air updates. Tesla's changed that game. I want my car to improve its value for me over time, because that's what all my other devices do. Right? They're over-the-air updates. So how, from an operational perspective, how am I going to get updates over here to this infotainment system? A lot of that system engineering design, but it's not just infotainment, it's other aspects of the vehicle. But those are important considerations and end user considerations that we have to think about. So when we think about these different kinds of customers, by the way, we don't just have customers in the operation value stream, we also have customers in the development value stream. There's a little mini operational value stream. We used to have them here, but I took it out to kind of clutter the diagram. There's a little mini operational value stream here. I have to hand off my infotainment. I'm over a supplier in automotive, and I have to hand off my assets to my OEM or whoever's consuming my work, the customer, the user who consumes your work, right? Whoever's consuming my work, I have to hand that off to them. Do I want to understand better how I can enable them and get artifacts of them more easily and simply? Of course I do. So if we look at this, we have good design thinking practices. We can do Gemba walks. We can go to places where the work is done. If it's in the operational environment, in the development environment, we can go to the consumer of our work and say, how is it you consume our work? And could we find a better way to do these kinds of handoffs, right? As Deming tells us, right, the handoff batch is the biggest one. So we can do personas and empathy maps and journey maps, all that other good design thinking stuff to better understand those customers. Cool. Once we understand our customer, we have to design the system. And frankly, this is the biggest challenge I think we have to our system development. So we've discussed the why we need to change, what agile product development looks like, and then next we want to talk about some specific practices. And probably one of the biggest ones is we have to specify the system incrementally. If you do what's called a value stream mapping, where you look at what's the time it takes to request a change to get it deployed in the operational environment in the customer's hands. A lot of times when we do these value stream mappings, we're engineers and we're looking at, okay, can we do a build faster? Can we do testing faster? We do a lot of manual testing. Can we automate some of that? When really the biggest delays are waiting for the work to be specified or waiting to be deployed into the operational environments and running through all the compliance and whatnot stuff. So if we're thinking about trying to move faster and be able to get those faster feedback cycles, specifying the system is one of the critical places to look. So while we need to certainly have all the activities of the traditional V, that's the wrong mental model to think about how we have to specify the system, right? So instead of thinking that we have to have a huge set of requirements and understand all the requirements of the system before we start architecting the system, and then understand all those architectural design considerations before we start building it, Agile takes a different approach. That let's just start building something now. The Wright brothers didn't wait to specify the plane. I mean, Langley did. Langley specified a plane that was never going to fly. The Wright brothers set about implementing small increments of value to learn, right? So we need these small learning cycles. So certainly our systems are going to start out with some number of constraints. We're starting with a car. The car will support 4 passengers. It will get it's going to have 4 tires. There's certain fixed things that you know up front. There are other things that we'll have to decide by the end, but we don't have to decide today. What's the fuel economy going to be? What's the towing capacity going to be? Those things can be decided over time. We might want to start up front with some kind of variable requirement. The fuel economy is going to be between 30 and 45 miles per gallon. The towing capacity is going to be between, I don't know, whatever the number is. So we might put ranges of values, and that's why we show this fixed variable, right? We start out with a set of variable requirements with some set fixed, and then over time, kind of like the Wright brothers, we do experiments and we learn along the way. We have a backlog full of experimentation along the way that we eventually end up with all those decisions made, and we have our car or our flying machine, whatever the thing we're building is, right? And that's why, so we have in SAFe this thing called the solution intent. You can barely read that, but that's where we manage all these requirement specification, requirements, designs, traceability between them, test cases. And that's where we manage all of that information. And then those decisions, the unknowns, drive the backlog items like we saw in the Wright brothers, right? Well, these are unknown uncertainties. What work has to be done to go validate those assumptions? That's backlog items. Some decisions we've made, so then we still have backlog items to go build those parts of the system. Once we decide on a design or decide on a requirement, then we still have work to go actually build that thing, whatever it is, right? And then roadmaps just take that work and they forecast it over time. We also want to think a little bit differently about requirements themselves, about any of the specifications themselves. In traditional requirement specifications, we had one place to put the requirements. Right? The system is going to support 5 people. The button on the screen is going to be blue and in the center of the screen. Those are kind of 2 different level of requirements, right? One is probably a high system level requirement. The other is more detailed requirement, right? The button's going to be blue. I don't want my system engineers to be making these decisions and then hand them off to the teams. That's too detailed, way too detailed, right? I mean, I ask people all the time, what's the longest delay you recall from when you specified a requirement to when somebody's actually going to build that requirement? Right? I've worked on a NASA program, for example, and in that NASA program, we had 5 levels of requirements. Before we could start building, that was the first phase, right? The first 9 or 12 months was come up with this very 5-level deep requirements hierarchy. The button's going to be blue kind of requirements, right? We don't need to do that in Agile. Why? Because we have another place we can store requirements. It's called the backlog. Okay, so certainly some of those system requirements, the ones, the high-level shall statements, the things we have to validate for a requirement, we have to verify those things for requirement specifications. Those shall statements still exist up here. But a lot of the detail, we don't have to decide those. We're going to let the teams, this intention is going to drive them to come up with those things. And they're going to, you know what, they're going to come up with those requirements at the right time. It's going to be features and stories. They're not going to define them all up front. They're going to define them at the appropriate time, closer to when they're going to actually build the system, right? So there's not a lot of, this is typically was a bunch of waste. We built a bunch of requirements that we just had to change downstream because we defined them 5 years before we can actually implement them, right? So it's important to understand that we have 2 kinds of requirements in Lean and Agile. Certainly we still have our shall statements. Those things don't go away. We need them. But we also have this second one that's more managed by the teams. These things come and go. They can be discarded. As we implement a story, we discard it. If we want to change the way the system behaves, a new story emerges and it pops up. And then we might have as part of the acceptance criteria those features and stories that if you have changed any of the shall statements or designs, if you change any of the specifications, go back up and make the modification, right? This is always true, right? We have to make sure that this is always true. Right, the next thing we have to support for this fast learning, right, this continuous learning approach is designing for change. Something we've known in software forever, right? I remember my younger software days, component-based design was a big thing, and it's still a big thing, and well-defined interfaces, components with well-defined interfaces. We had a bunch of technologies we were defining interfaces with back in the day. Corba was the first thing back in the 90s, and it's evolved to where now we have microservices, with web-based APIs and easily accessible, so that software has really latched on to this components and interfaces thing, and it's just now in the DNA of everything we do in software. We need to think about that way in hardware as well, because not all the things we change are going to be in software. So hardware certainly has components, and hardware certainly has interfaces, right? And the advantage of components with having components with well-defined interfaces is allows independent design iterations. So if there's an interface between these 2 folks, then these 2 can independently evolve their designs. We'll get an example on the next slide here. So we have that camera, right? There's a camera for autonomous driving, and it has to send a signal. It has to send that HDMI signal to vehicle control so it can process the camera. That also has to be mounted on the vehicle body. Well, we can evolve our designs so long as we don't break the interface, right? We start out with a dev kit, and then a rev of hardware, and another rev of hardware. We can keep upgrading our internal components as long as the interfaces stay the same. And also the interface allows us to do some early testing. Certainly the digital engineering, we'll talk about a little bit later, is certainly a big push in big system building and cyber physical system building. We're doing simulation early to try to learn earlier in a virtual environment. So we can take our models here and we can run some analysis and simulation across them to make sure that the weight's going to support the weight of the camera is going to be supported by the body, the heat transfer, or whatever the connection properties are, whatever these physical joint properties are. We want to be able to make sure we meet those things. I know what happened to the title of the slide. Apologies for that. Anyway, the title of this slide should be that we have to come up with an optimal solution design. We have to balance the needs of the operational environment plus the needs of the development environment. And the sentiment is this, that so often we design for the operational environment. If you look at automotive, for example, they talk about all the ECUs, electronic control units, right? What those are a bunch of custom ASIC parts that are built into the car to control braking, to do algorithms for braking, or to do emissions control or fuel injection type things. And they have logic in them to go out decide when to brake and when not to brake, or when to inject what amounts of fuel inside the cylinders and things. But the logic is fixed, because with an ASIC device, once you manufacture the part, the logic cannot be changed. So what's good about ASIC parts? they are cheap, they're low power, they don't generate a lot of heat, right? So there's some good properties to them, but they're fixed. Well, if I want to do over-the-air updates to change the behavior of my car, how am I going to do that when all the logic's fixed in all these ASIC devices, right? So really, that's the development world down here that says, oh, I want to push changes out to the operational environment. Well, that's okay. We've optimized for operations. We haven't optimized for development and fast feedback. And so often we don't look at the cost of delay, right? Another important Reinertsen thing. That, you know, if you quantify anything, as Reinertsen tells us, quantify the cost of delay. What's the cost of delay? Because we're not going to learn, right? That's the point. So maybe we want to, instead of using so many ASIC devices, maybe we want to use more programmable devices like an actual CPU or an FPGA, right? And build those things into the vehicle. Okay, and you actually, that's a trend I think you're seeing in that industry now, because they understand that they have to drive down costs. They've basically shot themselves in the foot to be able to get feedback and be able to do things like Tesla's doing.
So Harry, we have a few questions if you'd like me to jump in here.
Sure, yeah.
Okay, so the first one, I have been away from the DoD, or large system development work area, for around 10 years. But when I left, systems and software development standards such as DoD-STD-1679A or MIL-STD-498, DoD-STD-2167A, and DoD-5000 were required at various times, which mandated a phased approach with major milestone reviews between phases for large programs. Have the current DoD systems and software development standards evolved to accommodate agile practices?
Two things. Yes, they have evolved greatly. Thank goodness, right? For those of us that have been in that space for a while. But even still, 8 or 9 years ago, we were doing things incrementally. And basically what we would do is, where's the cadence? Let me look if I can get a cadence-based example here. Where's the slide? Yeah, right here. We'll just pick on this one right here. So if there was a bunch of cadences out here, we would call these incremental reviews, right? Certainly we had to do people know the government milestones. You have to have a PDR, preliminary design review, or SRR, the software system requirements review, PDR, preliminary design review, critical design review. You had to have these, and it was like, I think it's actually an act of Congress, right? It's in law. So what we did is we said, well, instead of doing, nobody said you had to do one review, right? Let's just call this first couple the requirements reviews, and the next 3 or 4 the design reviews, right? So basically, we turned these increments are incremental milestones. Every 6 weeks, every 12 weeks, we're seeing the system that we have built, and we called these the incremental review milestones. In fact, there wasn't even a term for it. ICR, incremental capability review, I think is what they call them. Then they map PDRs and CDRs, those incremental capability reviews. So not only and since then, there's all kinds of new guidance that the government's come out with internally to make that, you know, more obvious and make it less risky, right? It takes an aggressive program manager to be able to kind of risk their career, their job, to say, I'm going to do something differently, right? That's not being different is not incentivized in, you know, cultures like, well, the older culture of the government, right? I think the whole culture of the government's changing, where they are encouraging people to do new things. And certainly there's one of our biggest missile defense systems being built today is doing things incrementally, right, in the Air Force, right? So it certainly has changed, and that's a big weapon system, and they're doing things on an incremental cadence. All right, yeah, good question though. Thanks for the question.
You mind if I ask a couple more? Is it a good time?
Sure, go ahead.
Okay. How does the type of project that you were just speaking of affect how this approach is used? For example, life-critical things versus applications.
Yeah, certainly. So life-critical applications like cars, for example. So we're going to do things incrementally. It's life-critical things like automotive. I'm going back to that slide again. It should just stayed here. Right. If we look at incremental development here, with our life-critical things, automotive industries have been doing this for a while, or space, right? How often does SpaceX launch a rocket? They do it every 1 to 3 months. NASA, the NASA programs I worked on, it was 5 to 7 years. Start the program, we're going to have a launch in 5 to 7 years. SpaceX launches every 1 to 3 months. Likewise with Waymo. Waymo, I happen to live in the Phoenix area, and Chandler is where Waymo has been testing all their autonomous driving cars. You go to Chandler, Arizona, and you can't sit on a corner for more than 3 minutes without seeing a Waymo car. They're just all over the place. They're like ants. But I ask often, how frequently does Waymo update the software in those cars and the hardware in those cars? Right? Is it every year, every 2 years after they've gotten it completely certified? But I shouldn't say completely certified. Have they gone through a slow certification process, or might they update that software daily, right, and update the hardware as frequently as they need to update the hardware, make changes in hardware? And certainly, all those changes have to meet NTSB and ISO 26262, all those types of requirements, because that's the state of the practice. If there's an accident, people are going to start pointing to, oh, you're updating software every day. What, you were negligent. So they certainly have to meet those regulatory and specification requirements. And that's happening today. People are doing it, right? Just like the government question we had before. It can't work here, but in fact, it can and it does. It just takes that, that thinking outside the box type mentality to, and also just look at what other people are doing, because people are doing it. All right.
One more.
All right.
Have you ever found that sometimes you get locked in or have technical debt when you have to iterate to a better solution?
Yes, absolutely. That's why that's the whole agile concept of refactoring. If we take a one design approach and we find out that it's not the optimal approach, we have to move. We will have to modify infrastructure, probably, likely. We'll have to change our designs, and that is frankly, it's critical, because a lot of times we think about building the system one time. Build the system one time, put it in operation, and then we're done with it. And the systems that we build, we're never done with them, right? We're always evolving those systems, right? I think that's a different mentality. That's why SpaceX and Tesla are different. They didn't look at trying to build one rocket and launching it. They tried to look at how can we build rockets better, right? And that's we'll talk about that in a minute, actually in about 4 or 5 slides, where the factory is the product. We're not trying to build a rocket. We're trying to build a system that knows how to efficiently and effectively build more rockets, or in the automotive example, build more cars, or whatever they are. We want to create a system that knows how to build those systems repeatedly. So we're not one and done. We're trying to take that mentality away. Right. We'll get to that slide here in a minute. So the next important topic is we want to frequently learn faster and to be able to validate assumptions. We have to frequently integrate the system. Great video here. You can click on that link. I don't know if we make the slides available anyway, which I assume we will. Where Jim Bridenstine is talking about what NASA has learned from SpaceX over time, right? Here's the NASA approach. NASA before, why it took 7 years to do one launch, we had to fully qualify every component and every subcomponent and every rocket. It's fully qualified. It's got to go perfect. Every launch has to go perfect, right? And that slows us down, right? He points out that Tesla's willing to go fly, test, fail. Get something and let's launch something. How fast can you get to the next launch? How fast can you get to the next launch? Right? That mindset's critical to learning, right? That's the goal. Those who learn faster win. And I ask this all the time, right? Well, what could you learn if you could take the changes you're doing now, whatever it is, and put them in some kind of operational environment to test it? And every 2 or 3 months you could do that. What value would you get out of that? And then thinking, shifting left, what would it take? And so example, like with SpaceX, what did it take for SpaceX? Took some really creative stuff, right? Engineering and production are in the same place. The engineers are designing the next part, and the next part's going to go on the rocket, manufacturing. So engineering and manufacturing just right there together. How do I manufacture parts that quickly? Well, Tesla has the world's largest, they commissioned actually the world's largest 3D metal printer in the world. And they got it down on site so they can manufacture nozzles and fuel tanks and other kind of parts. So they didn't have to wait to get them manufactured and shipped by rail over to Texas. And so they just eliminated all those delays, right? Again, thinking out of the box. How can I learn faster? We'll talk about the wild success SpaceX has had. Again, digital disruption in space, it may be over. I think SpaceX, they're another Amazon, frankly. They've taken over. Now it is true. So when we think about frequently integrating, hardware domains do experiment. It's not like we just design our part and manufacture it one time. We have equations. We do models and simulation. We connect parts with breadboards. We do this kind of experimentation stuff. But historically, it's kind of done in silos. The mechanical people are like, this is our camera, right? The camera, well, one person's doing the enclosure, and they're iterating over their designs, and somebody's designing the printed circuit board that's going to house the optical chip, and then an FPGA. There's an optical chip that we're getting from a supplier, an FPGA. Somebody's writing the analog to digital logic that has to go in that FPGA, and then somebody's designing the circuit board to hold those two, and they have revs of their hardware. Well, instead of working in isolation, that's why we put them on the same team. You're building a common part. Let's integrate your solutions every as frequently as we can. Let's the integration points control product development. Great book by Don Osterwald. He was an exec at Harley. Again, this is back in the 90s, pre-software, right? Wasn't a lot of software in Harley's back in the 90s. He looked at Harley programs within Harley Davidson that were successful and the ones that failed. And the ones he saw that were successful had smaller incremental cycles, right? He looked and said, well, the ones that are successful have these learning cycles, right? And he could tell by the purchase orders, right? He looked at how do you know that hardware companies are incrementally learning, because they have to get the new parts to bring them in to assemble them, right? So he looked at patterns of purchase orders, and the ones that had fewer time between sets of purchase orders were the ones that were successful. The ones that had longer times between sets of purchase orders were the ones that were failures. So interesting observation. And that's why he went and put Harley Davidson on a common cadence, back in the late 90s, maybe mid 90s, I forget, whenever the book was written in 2000, but it's from his work in the 90s. And that's why you see in automotive. That's why we apply this common cadence. This common cadence across an entire organization. Those are the learning cycles, right? To integrate the system. And then we don't just stop at the team level. We go to the team level, right? How can we take this learning and put it into some environment by which we can learn better, right? We put this in every increment. We're putting these changes, hardware and software, into some kind of operational environment. Maybe it's a vehicle that runs around a test track. Nowadays, it's Waymo putting them into, the car that's running around Chandler, Arizona, which we just talked about. Right? We need to get validated learning from the operational environment to get feedback and all of right. We have to make this safe, right? I was actually on a call with one of the big three automotive talking about this just this week on Monday. Well, I guess it's last Monday. And they brought up some common safety concerns. And absolutely, you've got to. We can't put software into a car that's going to rapidly accelerate the car and kill a driver, right? And so, certainly you have to have all the rigorous testing and verification validation done. And that's why that automated testing, verification, validation is so critical. Okay. So, and then at the end of the day, we take all the value streams that contribute to these vehicles. This is kind of an automotive industry. We're back now to that automotive supply chain, all the suppliers that are supplying in that supply chain, which includes our little camera team, but it's so much more than that, right? It's 10,000 people or more contributing, and that's why we have this common cadence. Now, not everybody is going to be contributing everything every increment, right? We're not going to get a new engine block every increment for sure, but we're probably going to get new engine algorithms and calibrations and things like that integrated. And they integrate oftentimes to more than one customer, right? So the powertrain here, I'm building a product line of powertrains, not just a single powertrain, but a set of them. And they're being integrated into one or more of our vehicle programs. Trucks, sedans, I don't know if they make sedans anymore, but trucks and passenger cars and SUVs and those types of things. All right. The goal of all of this is really to shift learning left. Why do we integrate more frequently? Why do we want to design for change? Why do we want to have smaller batches of specifications? Because we want to learn faster, right? We want to shift that learning left. And go back to that traditional approach versus NAST approach. Here we see those traditional phase gate requirements, right? These milestones didn't gain us any new knowledge, right? And that's the great Alan Ward, another great book. Alan Ward, by the way, I think he was Dontar's advisor, PhD advisor back at University of Michigan. And his book on product development, lean product development, great. That's another great book, by the way. But he talks about more that development is more dependent on what needs to be learned. I love the word learn, right? Than what tasks would be completed, right? These were focused on tasks. Do all your requirements so I can review them. Do all your designs so I can review them. I didn't learn anything. SpaceX instead, let's launch a rocket and see how it goes. What did we learn? Let's launch the next one and launch the next one. So how do you make the ability to launch rockets this quickly? right? And that's really that quote by Elon. As much as I don't like quoting Elon anymore because he's become kind of a goofball, he still did a few things right back in the day. The factory is the product, right? I think most of us have probably heard that quote, or if you haven't, I think it's a great quote, that it's the machine that builds the machine, and it's the latest version of the machine that builds the machine. He's not trying to innovate. He's not just trying to innovate on a product. He's trying to innovate on the machine that builds that machine, and that is just so critical, right? I think that's what software has been doing in it forever, right? And let's take a look at the next slide. Software has spent the last 20 years of Agile to build the machine that builds the machine, right? That's the Google site reliability engineers and Kubernetes and platform as a service and all that infrastructure. If you back up, when I was writing code 20 plus years ago, we had jar files, and we had, we could do component-based architecture. There were some interfaces between things, and you had virtualization, kind of VMware, where you could, but it wasn't but you still had to spin up whole threads and processes, and anyway, they took those technologies, right, the virtual machining and the notion of component-based architectures and interfaces, and they took it and they really built a lot of great infrastructure. So now that it's the standard, right? It's well known, it's documented. You can get it off the shelf even. I think we're still learning what a hardware CDP looks like, right? What's the factory? The machine that builds the machine. The factory is the product, right? So software had to build their product for sure, but they also spent the last 2 decades building the machine that builds the machine. We're doing that same thing now in hardware, and it has different elements to it, right? So there's the virtual environment, and that's where we learn in the digital environment. Big push for digital engineering. I'll talk about that later. There's also the prototype environment. Well, actually, I got a slide to talk about that. So I'll explain it here. I have a slide on it. Right, this is the digital environment where we can do modeling and simulation and trying to connect more integrated models and do digital threads and digital twins that exists here. You can't learn everything in digital environments. Sometimes we have to go to a physical environment. That's where we do our prototyping, right? So we do mock-ups and prototypes and breadboards and those types of things, and that feeds back into the digital environment. Whatever we learn there goes back to digital. Last but not least, we want to put those things into a production environment as quickly as possible. Get that out in the streets of Detroit or the streets of Chandler, Arizona, to go test those things and bring them back in here as well. Okay, so these two together, right? Eventually the software has to also go into production and operation as well. But those two together, that different types of components will follow different continuous delivery pipelines, so we call those things in SAFe. And that's where I think where a lot of innovation is happening today. A lot of innovation in digital engineering, a lot of innovation in 3D printing. In fact, today, you can get a printed circuit board turned around in a day, right? There's places where you email them a CAD file, and they will next day will ship you your printed circuit boards. So we don't have to have all the skills and equipment and technology necessary to do those kind of things. They're available to us today. Or it could be like SpaceX and just buy the world's largest 3D printer in the world, and then you kind of done your manufacturing operation. You manufacture and produce right there on the site. Do want to make a shout out to General Motors was a great example of this. The CEO of General Motors challenged the product team to make the Hummer EV in 3 years. Right, I want a vehicle in production that somebody can buy in 3 years. And they pushed back and said, we've never done that. 5 to 7's our best, and there's all kind of newness here. Right, it's going to be an electric car. We don't have any electric cars yet, but I want my first one to be a Hummer. So a lot of uncertainty, a lot of unknown, a lot of risk, right? Back to that idea, right? Challenging goal. I'm not going to tell you how to do it, right? I can't use project management to get this done. I have to use Agile, decentralized decision making, and let you guys run. And certainly they got it done. They had a prototype. They had a prototype on the test tracks in 18 months, right? Record time for them. And they if you read the literature, they'd say one of the big reasons they were able to do that is there was a digital engineering research group going on at General Motors already, kind of a research area, and they pulled them in and said, we're going to be your first customer. And so they did a lot of learning. They had a lot of integrated digital models in the hardware space. And it was fortunate too, because COVID hit right in the middle of this. So fortunately, they were already working in a digital environment because they all had to go home. So they got it done in 3 years, even despite the pandemic. Right? Very impressive. Anyway, big investment, not just in General Motors, but in a lot of other places in digital threads, digital twins, and digital engineering. This is just a kind of a throw in, right? And as we all know, that those environments validate each other. I've heard that from not just Joe Justin Wikispeed, but Volocopter. They're doing over in Europe a transportation as a service, right? It's helicopter taxi basically. They have such rich digital environments over there that they don't have to recert. Every time they push changes out to the operational environment, they don't recertify them. Right? Their digital environments have so much built-in quality that they are pre-certified, if you will, however you do that over in Europe anyway. Here's kind of the business outcomes. I kind of saved this for last. If we back up 10 years ago, these are kind of all the NASA launches for the various blocks. And SpaceX did 5 of them 10 years ago, and the other suppliers, other space providers did the other 80% of them. Now it's kind of game over. Yeah, SpaceX does almost all the launches because they have learned how to buy down the cost of launching. They can launch quickly. They can launch way more cost effective than anybody. Right? They bring the rocket back to Earth. Right? They have it land. I remember, but about 4 or 5 years ago, they had that where the two booster rockets came down and landed on the launch pad at exactly the same time, almost as if it was scripted. I've been told it wasn't, but they did investments in all that learning and stuff. It's just really cool stuff. And they won, right? They won the race to digital in space. It's theirs to lose at this point, I would argue. Another important point is, again, I hate Elon quotes, but he does some things right, so we got to give him credit where credit's due. That this is a change in culture, right? You have to look at the culture of the organization. I'm glad that somebody brought up that question about the government, right? Because the government culture wasn't one that worked this way, right? It took a lot of doing internally and people taking risks and having the courage, right? One of those agile values of courage to go off and try new things and do things a better way, right? Work differently, change the way we're going to work. That takes courage, right? And we need an environment and a culture that enables it. And this is just a great example of that. That not all these launches are successful, and certainly this one a couple of years ago failed spectacularly. Anytime a big rocket crashes, that makes national news headlines and everything. And of course it was, but quickly the leader of that company, said, hey, yeah, there were some reasons that it failed, but we got all the data we needed, right? So it may look to the rest of the world like it was not successful, but it met its goal, right? It met its goal. We learned everything we needed to learn for the next launch. And yeah, this thing crashed. Doesn't bother us because we're in the process of already building the next one for the next launch. We probably weren't going to build the whole thing. We're going to have to rebuild that casing and stuff. But they planned for this. What does a RUD stand for? They have a term for this. It's called Rapid Unplanned Disassembly. RUD. So that, in other words, a crash. It's so common they've got an acronym for it, right? And they've designed their environment to be able to handle RUDs, right? And so they're from a business outcome perspective, right, they get all the launches because they invested the time and resources to understand how to make launch more efficiently. They would argue build a CDP, a continuous delivery pipeline of physical CDP to be able to do that more quickly, more effectively. Right. And with that done, we still have a few more questions. Time for questions if there are any.
Well, there's one that's specific to tools. They want to know, is IBM making investments in their ELM product to support the use of agile practices on large system software development, or are there other tools that are better suited for the transition to an agile approach?
I wish I could answer that. I have been out of the tooling space for 5 years, so I'm not qualified to make that assessment.
So we do have another gang member on the line. I don't know if Peter's on the call. I don't know if he can unmute and maybe answer and address that. I don't know. Peter, I don't know if you can hear me and if maybe you can unmute. I did ask him, and he said that IBM is, and that they talked about it. We had a meeting back in October, and he said that they are, and that they were talking about it at our summit. So I don't know if you can unmute Peter and elaborate, or if we'll just go with that.
That's a good answer. Yeah, or if Peter wants to come off. But that sounds like the answer.
Okay. So I guess we're going to go with that. Oh, he said he cannot unmute. I'm trying to unmute. Oh, there you go, Peter. I think I unmuted you.
Okay.
There you are.
Yeah. we were 321 Gang was at a session with IBM just recently, and they talked an awful lot about this kind of thing in general. You know, how they're supporting the digital twin, you know, all this move to digital and agile and so on and so forth. So they are investing in their tools to do this kind of thing. Now there are other tools that are good as well in terms of some of the same aspects. Atlassian has been doing a number of things with Jira Align, and so on and so forth to help with this kind of stuff as well. So IBM is doing a real good job. There are other folks that are as well.
I literally just saw the Gartner report for I think it was portfolio tools, and
Right.
the Atlassian was in the top quadrant for for agile tooling, the portfolio agile tooling, and the IBM stuff. The recommendation for them was for engineering, right? They have the engineering tooling, that no one else has, basically.
Right.
What I read from it anyway. Yep.
Very much so.
Great. Thanks for that, Peter. I appreciate it.
And they integrate with each other, as Peter probably knows well too.
That's right.
Okay, so let's read another question here. How does SpaceX justify the cost of launching so frequently? I want to know how to explain the added cost for testing in the operational environment.
That's that's kind of this slide that I wish I put a title on. A lot of times we assume we're going to be one and done, right? So we over optimize for the operational environment. It's expensive to go to the operational environment. Well, it is until you find a way to reduce the cost, right? How did Tesla do it? SpaceX, mixing my words here. SpaceX figured out how to make rockets reusable. It's very expensive to launch a rocket and not relaunch it, right? So they were able to bring parts back. The booster rockets, I remember 5 years ago watching those things re-land on a platform out in the ocean. Right? Probably landing on a platform in the ocean because they didn't know if it was going to be able to land properly or not back then. And then eventually they have the other rocket assemblies that they're able to go to space, do their work, and then come back and be able to be relaunched. So they invested early in learning, right, with those fast iteration cycles, right? So we think so much about being one and done. We're going to define the system once, and we're going to make that system and we're going to deploy that system and just be done. The agile approach is do things in small batches and learn, right? Launch early, launch real quickly and learn. Launch more quickly and learn. Launch more quickly and learn. And certainly the economics are there, right? This is the second to the last slide that, SpaceX was, they were still, even back in there's a list of Wikipedia page of all the SpaceX launches, right? They were still launching frequently back here. Some of them were spikes and learning, and some of them were actually real launches for NASA. But over time, right, those spikes for learning have grown into, now granted, this is kind of old data, just up to 20, where they do all the launches for NASA now. So I would say that you have to understand the cost of delay. I would argue that the people down here didn't understand the cost of delayed learning. They were too afraid. They didn't have the courage to take the risks, to go off and invent a new way of doing launches, and they became disrupted, right? So that's the class, from years ago, that book from decades ago. They're being disrupted because somebody found a new way of doing it, because they didn't have the courage or to go do that. And the culture, right? A lot of it's the organizational culture that you're describing. I don't take risks. I don't have the courage. It's too hard around here to make change. And startups like SpaceX are able to take that away from them. It's kind of a long answer, but I hope it got to the question.
Yeah. Okay, well, it looks like it's the top of the hour here. So our webinar is concluded, and I'd just like to let everybody know that if you have any additional questions or comments, please feel free to email us at info@321gang.com. We did record the webinar, and you can share it with your colleagues. It will be posted to our website next week. And if you'd like to check out any of our previously recorded webinars, go to 321gang.com and look under the resources tab. We have quite a few. So thanks everyone for attending, and thank you so much, Harry, for your presentation. It was awesome.
Hey, my pleasure. Thanks, everybody.
Bye.